on what kinds of things that you've learned during the year. If you've kind of been following EOAS as well as perhaps other departments too, everybody's kind of interested in like, okay, what are the things that we want to do, in teaching course, and then what have they, what has everybody learned during that course? And they often give you forms and stuff like this, but I think it's actually quite useful to do a self-assessment. And the way to do this is I'm going to give today, in pretty quick fashion, basically the same material that we did on the first lecture. So if you remember that first lecture, we did that geophysical tour through Ireland. And there was like 6 different kinds of survey techniques with 6 different kinds of problems. And I'm sure that almost everybody that was sitting here is like, I have no idea what's going on. So there's lots of terms, lots of words that you would not have heard before. And yeah, just a little bit mystified. So now we can revisit exactly that same thing. And you'll see that, oh yeah, I get it. I know. I can see the problem. I can see what survey they're doing. I can understand what physical property they're working with and the information that they get out. You're comfortable with all the terms. I think that alone is actually a good metric for deciding, okay, what have you done? Or what have you learned? So anyway, that's kind of what I want to do. This was actually from the engineers. 2 years ago, they set up something, put a 7-step solution up on the what do you call it, thing that they always burn up there. So I thought, that's kind of nice. So here we are. We've got a framework, 7 steps. Everybody knows what they are. And I thought you guys did a really good job of presenting your team projects within the context of these 7 steps. The first case history that we looked at was trying to find that till layer in Dublin. So that was there was something called a lodgement bedrock underneath, and you were trying to find that dependent upon the stiffness of what was going on. So we had various elastic parameters, bulk modulus, shear modulus, P wave, and S wave velocities. And the idea was to try to find till, which had variable velocity overlying a high velocity limestone basement. And there was a number of different waves, like S wave, P waves, and then 2 surface waves, Love and Rayleigh. They all have different particle motions. And the survey was one in which went into downtown Dublin. They had this device here, which actually had a weight drop on it, and they had seismometers out along here, and they measured basically it's the surface waves that they were interested in at the different geophones. The processing involved in that, in MASW, is a little bit complicated. We never really looked at that, but basically you take these data, you convert them to phase velocity, and then you invert that to get this image out here. So this is depth, this is horizontal distance, and it's coded in velocity, so red is high velocity. So you can see how where that perhaps limestone is, and here's that till layer on top, and you get some idea about the thickness. The seismic also had a number of other things. We had seismic reflection that we could work with, as well as seismic refraction. So we spent a fair bit of time looking at those guys. If you have an experiment where you have a source, and then you have receivers or geophones out here, then you get some direct waves, you can get some reflected waves, and you can get some refracted waves. And we showed how you could do travel time curve analysis to get both the velocities of the different layers, and then using the intercept times, these guys here, that would give you some information about the layer thicknesses. So the velocities came from the slopes, the thicknesses came from the intercept times. The seismic reflection, which is used both in geotechnical and almost primarily in the oil industry, was one in which you have a transmitter sometimes it's a vibrator truck, sometimes explosive, and a whole bunch of receivers out behind you, and you gradually move this thing one way or one direction, and then you're successively getting reflections off of particular points here, and then for each of those shot gathers that we have, you get something that looks like this. You get direct waves and surface waves, but you also get some reflections. And if you line those reflections up doing an NMO analysis, you see that, oh, they're all kind of stacking up here like this, and then you sum them up like that, so you stack them, and that gives you then a final section, which we saw look like that. So this was a CMP processed section. It's got some reflection events that come in here. So that big one is probably the base of the alluvium, and there were some other things that cropped up. So that was the seismic. We then went on to look at a different problem, and this was to look at, see if you could find sand and gravel quarries. So sand and gravel has got a low velocity. It's also got, it's very resistant, so it has a low conductivity. And you know, you're faced with terrain like this, and you're trying to sort of determine in this whole bog area where there might be sand and gravel deposits. So because as I said, the bog material is wet and conductive, gravel's deposits are very resistive, we could do both an EM and we could do a seismic. So from the point of the resistivity types of calculations, we've seen this diagram here before. It kind of shows many orders of magnitude, 8 this example, orders of magnitude difference between really conductive material and really resistive material. And what we're interested in here is finding areas of resistors. So as a first reconnaissance, they took this simple electromagnetic device, it's called an EM31, which we've seen a lot of, and just sort of walked the whole area with this guy, and then plotted up the apparent resistivities. And you can see the blue values in here are regions that are really quite resistant. So if you're looking for sand and gravel, you know, probably these guys here that are intense blue, those are particularly good areas to look at. So pick one of them, and you could go along and do additional survey now, a bit more follow-up. And what was done here is a DC resistivity survey over top of this line, and then that's inverted to get this colored section here. The blue is resistant, so you can see along this particular line, there's a region here that's quite resistant. So that's very likely your gravel. So that's good. So that helps answer that question. And in fact, there was also some seismic analysis that was done, and it got these layers here with this as being a base. So that was a case of doing kind of a reconnaissance and then a bit more of a follow-up. One case, you start reconnaissance with an EM, and then you do a DC resistivity survey, and then some seismic. Mapping the peat thickness. So peat is basically a carbonized fibrous material, right, with a large amount of water, and so it is very distinguished by what its dielectric constant is. So there's these peat bogs that exist over very large areas. They still actually burn a lot of peat in Ireland. I was surprised to hear about that, but they do. So they actually mine this stuff up and they dry it, and then it's used to fire up your stoves. Doesn't sound like it's got a very low carbon footprint, but I think that's what they're doing. So we're interested in the dielectric constant, and we had this table showing that different materials have different dielectric constants, but the main thing was water has a dielectric constant of 80, so it's very sensitive to that. And the system that was used was one where you have a coincident transmitter and receiver. You simply pull that guy along, and you get signals out that tend to look a lot like seismographs. So the system that they use, there's a tractor here. They're pulling the GPR system along here. So that's putting energy down into the ground, getting it back. And we've got to have ways of keeping track of where the vehicle is at any time, and so they use GPS. So they've got a 100 megahertz antenna here, and then they're recording data every 20 centimeters along these lines, and then about 70 meters between the lines. When they get those data, they look like this. So it kind of looks like a radar section. This axis is in time, but it's in nanoseconds. This is distance along here, and you get some kind of a set of reflections that go along here. So here's your difference between highly saturated and unsaturated. The only processing that's really done on this to try to make it back into something that's geologic is to take account of the fact that, oh, when you're collecting the data, you're actually kind of going on topography. So you do that correction for the surface topography, and now you've got kind of a geologic section that shows a flat lying peat layer underneath here, and gives you some idea about what you've got there. And in the end, you can take that whole system and convert it into kind of a map of peat thickness over the area, and this is what you get. So you get some very large thicknesses here and smaller elsewhere. Another area that was looked at in this tour was to look at Karst Investigations. So again, we see that even in the lower mainland, there's areas where we've got limestone. It's been eroded. In this particular case, the limestone was eroded, and then it was filled up with material and water, so that the tunnels actually look more like conductive features compared to the limestone. So there's a couple of techniques that could be used for this. One technique that we never talked about was gravity. It's the simplest technique, but we just somehow didn't find a way to fit it in. But gravity is looking for density structures. And so if you've got a region of low density, then you'd have low gravity over it. The other is to actually look at the electrical conductivity. So that could be done with a DC resistivity survey. It could also be done with any kind of EM survey. In this particular case, they're going to use the DC resistivity, but they're also going to collect gravity data. So it's called microgravity data, which means it's kind of like high sensitivity, and they're done on instruments that can be, you can acquire data over a very, very small grid area. So in here they did a 10 meter by 10 meter grid. So what you're looking at here, this is a surface map. This red region in here is indicating low gravity values. So that means that there might be a low density material underneath here. So this is like a horizontal plane. And then along this line here, they did a DC resistivity profile and got something that looks like this. So the red is low resistivity, the blue is high. So the interpretation is that this dark blue are limestones, and then you've got something that's coming in like this. So you've got some kind of maybe a more karst cavity that's coming in here, and that coincides with the gravity. So you may have done a fairly good job on locating. For mineral exploration, they did have a couple, well, two examples in that in that paper. They were sort of okay, not quite what I particularly wanted, but I think you can go back and read those. I'm going to do a different one. So for mineral exploration, we're going to use a combination of DC resistivity and chargeability. So now the new physical property is chargeability. So that's the ability for rocks to actually accumulate charge when you've got an electric field on them. And different rocks have different chargeabilities. The big kid on the block are sulfides. So this is where, if you're looking for a massive sulfide, or if you're looking for many different mineral deposits, IP, induced polarization, IP experiment is one of the best. So as far as minerals goes, you've got pyrite, chalcopyrite, graphite. These are all very high chargeable materials. So in the case history in the book, they did looked at a particular area where they had a lead zinc. They did a DC resistivity survey, got the apparent resistivity, and they also got an apparent chargeability, which gave them some idea of what was going on. What I found lacking here was that they just plotted data. And you really, these days, we should be inverting data. And that was the example that I showed you in class. This was that area from northern Australia. There was like 10 lines of data that went across here. For each of those lines of data, we did a pole-dipole experiment and obtained pseudosections then that looked like this. So the red indicates something that's really conductive. And so you can see that there's a big conductor there. And at the same time, there was also, well, two different configurations. One was a pole-dipole, the other is dipole-pole, so we're just reversing those two things. The impact point here is that you want to make sure that you are exciting the object as much as you can, so you want to change the location of your sources or your transmitters to do that. And then there was also chargeability that was obtained with that. So they got both the DC resistivity and the chargeability. So here were your data, and then what I showed you in class was that we take those data, generate an Earth model that's got a whole bunch of cells of unknown conductivity and chargeability, and invert those, try to find a distribution of them that will give rise to these data. And when we did that, we found this thing. So inverting the DC resistivity, we got this great big conductor here. So that was geologically the big kid on the block. It's interesting, but not anything special with respect to mineralization. The information about the mineralization actually came in through the chargeability. And this is the final result of the chargeable inversion. And importantly, we've got this big guy coming in here, which sort of comes in about there. And this unit here is, as I say, is chargeable, and that is the one that is mineralized. The last thing was magnetics. Actually, it was the first thing in the course, but the last thing that we were going to talk about here. And here, physical property is the magnetic susceptibility. So the exploration area here is one in Quebec. It's called the Raglan area. There's surface contact here. There's outcropping ultramafics here. And if you do a magnetic survey over here, you get a couple of really big, high magnetic anomalies that are associated with them. So magnetic susceptibility was the ease with which a rock can be magnetized under the presence of an external field. And again, there's a whole variety of susceptibility ranges for each kind of rock, often a couple of orders of magnitude. So, again, by knowing a particular susceptibility doesn't tell you that it's either, a gabbro or granite or something else. So, but each type of these rocks has got a range of those values. So if we come back to this survey, here was the survey data, and those data are inverted, and they give you a model that looks like this. So what you're looking at here is a three-dimensional inversion to give rise to susceptibility that reproduces these data. The interesting thing from a geologic perspective here was that it was thought that these two regions, if I go back, so these ultramafics that are coming in here, they're mineralized. The geologic model was that they thought the mineralization was just coming up in kind of cylinders. What the inversion showed is that no, these units kind of come up, but they seem to join at depth. So it's almost like it's a bit of a flow unit. And that really changes the geologic model, especially for what their ore reserves are. So there was a hole that was drilled here, since it indicated there should be a lot of susceptibility. And that hole was drilled, they found a couple hundred meters of ultramafics, and some of it was mineralized. So that one inversion actually had a really big impact on the geologic model. And after that, and this was 20 years ago, every magnetic survey that's been carried out in that Raglan project has been inverted to give a 3D model. So that's kind of where we are. So what have we learned? Well, hopefully that geophysics has the potential to solve many problems. I think one of the most important things is that you need to really articulate what the thing is that you really want to find out. So this kind of comes back to, in the 7-step procedure, it's like step number 1. What is it that I really want to have done? Too often, especially when problems are complicated, they simply say, oh, well, let's try this and solve that. Well, life's not so simple. And especially now, I think that you've seen within the context of geophysics that you're not going to get perfect resolution about any physical property, and nor does the existence of that physical property tell you everything you want to know about your geologic or geotechnical environment. So there's a complicated process here, and you have to be accepting that that is. But that means that you need to articulate the question, and then now you can do the 7-step process. So, a couple final things. This is extremely important. Use geophysics thoughtfully, with all the knowledge that you got, all the background, and you just got to think critically. You cannot take for granted that, like, oh, I can just go ahead and do this and it's going to work. Because there's always little things that are problem dependent that kind of can throw a little bit of a monkey wrench into things. So you need to always be thinking and always be really assessing, what do I have, what do I need, and where am I at. But I think maybe the most important thing that you can take away as follows. Works. Okay, so here we go. Check that up. So we're digging with hands. Yes, interesting tool. Here we go. I've got a few more of these, but I'll tell you what. Before we get too carried away with watching movies for the next 15 minutes, I got a few things to say. One is that traditionally for this class, we ended up the class with my wife making cookies. I meet people years after we've taught this class. This happened. It was at some presentation at the Orpheum, and I met a student that I hadn't seen in a couple of years. He had his girlfriend or partner there, and yeah, so we reconnected, and then he was introducing me to his partner. And you know what he said? He had two things to say about me. Well, he said, okay, so yeah, I took 350 from Doug, and you remember I told you about the microwave oven, how a microwave oven works, right? So that was the thing, like, how did the microwave oven work? And then the other was, and you remember the monster cookies at the end of the class. Those were the only two things he took away from that class. So that's one thing. I'm going to pass these guys around, or maybe, I don't know. Look, these are really good, I'll tell you. Oh, they have peanuts in them. Is that okay? Oh. So traditionally, every year at the last lecture, distribute these. The other is that this one actually is a little bit extra special because this is the last time I will be teaching this course. It's also the last time I will be teaching any course at UBC. So this turns out to be the end of 41 years of lecturing. Woo. So check this out. Okay, I tell you, this is very fast, a lot of energy. Gosh, I'm impressed. Okay. Whoops, how did we do that? You recognize these people? Oh. It's just so hard. Oh. You can just feel that, right? Oh. You know they're slowing down? Have you noticed? Like we started off really fast, and then now we also have an administrator. Nothing. Oh, this kind of reminds me of the city of Vancouver, right? You got like one person who's actually doing something, and everybody else is like kind of hanging out. Throwing the sand along. And now, okay, so did you catch the first part of the We're using foot. Okay, so what have we got? Okay, so we got, first of all, the pointy end of the rake. We have our hands. Did we have the stick yet? There's someplace in there.
The hammer. That's a hammer.
Oh, the hammer. Yeah. There isn't sticks. I'm not sure that we've seen that. So good. Maybe it's coming. Well, at least it was a nice day. Whoops. Okay, so there we go. A couple of takeaways. So yeah, teamwork. Teamwork. That's it. It's important. Even if you have a hammer. Okay, so I think the hammer was a hit, actually. No pun intended. I think you missed the first part of that, but maybe it's a new tool. Ah, here we go. A new tool, right? Magnetometer. Could be. So what do? So while all your friends are digging away, you're sitting up there, kind of relaxing, holding this tool, magnetometer top. And you measure some data, plot it out. It's easier. So anyway, that's it. I just wanted to thank you. I wish all you guys success in your career. And the only request is invite me to your graduation dance. There's lots of cookies. There's a lot of cookies. Yeah, so as far as the final goes, it's going to be the same as the midterm. Yeah. Except it's now 2.5 hours long. But there's half multiple choice, maybe a little bit more, and some short answers that just try to make it fair. Okay. Ranking people on the basis of multiple choice is not all that effective. So, yeah.
Is the final mostly going to be on stuff from after the midterm?
Probably about there'll be a heavier weight on the stuff since the midterm. So yeah, you could expect a few more questions in there. Yeah, the other thing is that I will be here through all that time. So if you have questions, give a shout. Also, you have maybe emails of other TAs. So between Mike and Devin, Don, myself, we're around. The best way of getting in touch with me is email. So I can come in or we can answer questions. I think that's about it. I think aside from, oh yeah.
There was a prize.
Prize.
The one.
Well, okay. So there's two things that happen to the prize. First is, I wasn't sure that was a really successful thing. Like Alan had his card out today. That was one.
So give him a prize.
Well, I was actually going to do that until I got into work this morning, and my office is locked and the prize is inside. But I'll tell you what the prize was. And Alan's got a chance. I got a couple. 2 stars. Okay, so I thought the thing that might be intriguing was a puzzle. Are you guys puzzle freaks? Yeah. Okay, so what might have been if this whole process had actually worked with. Okay, so it's called the ultimate puzzle. And it also has 48 steps or 48 solutions. It is a sequence of kind of like jigsaw puzzle pieces that you have to put together in like a 4x4 map. Okay? So I brought it in, and I just set it on the table for the GIF group, right? And honestly, like Devin got in there. I brought it in before lunch, okay? And Soggy and I had lunch, and then we came back. I gave the class, and then I went back a half an hour later. Devin is still there, putting this thing together. Nobody has yet solved it. It's challenging, but it's the kind of thing that you can kind of put down and Yeah, play with. So if this whole experiment with doing the name cards had actually worked, which it did not, you know, there would have been a different outcome. Anyway, take a look. So what might have been if the whole experiment had worked. Okay, guys. So yeah, good luck. So what are you guys doing for graduation? What do you do?